Hi folks, this is a video in response to a viewer comment. This will be my last posting for the next 2 weeks because, like I said, I need to take care of other things. This comes from Patreon Andreas H. And basically what he did is he published a little paper where he went through my calculations, but instead of ending up with what I ended up, he ended up with a factor of 2 pi. So I'm going to post this paper and I'm going to post what I'm about to show you so you can look at this stuff yourself. So here is his paper here, and I'm just going to go down to the summary. And the first thing is he gets the right answer for both tandem SOSOPs at 0. Now I think he made a mistake here because the orientation of the SOSOP for the inertial field, because he's only doing the inertial field here. He's not accounting for the magnetic field. He's just doing the inertial. And the inertial field does not care about the orientation of the target. The only reason why I did that in the original derivation is to come up with this little factor here. I don't know if it's big enough that you can see. Let me blow this up a little. So they can show you that as you get very, very close, you have to start considering these effects. But once you look at the condition where d is much, much greater than the radius of orbit, then you can just worry about these components here. And in that case, you can completely ignore the orientation of the target. Okay, so you can treat the target as just a lump of charge equal to the charge of 1 electron. And all you have to do then is compensate or account for the orientation of the source. So what I've done is, and so the mistake that he made, and I'm grateful that he did this because it gave me a chance to go back and double check everything, and for all of about 10 minutes I thought I had a mistake. I do that to myself sometimes. I second guess myself. So the major mistake is this is the proper curve for what would be the amplitude of the vector that is seen at the target. The problem with it is it needs to account for the direction in the x direction. So in reality, this integral here should be cosine squared. Okay, because cosine will give you the amplitude of the vector, and cosine again will give you the component of that vector that is in the x direction, in the direction of your target. So if you do this with x squared, I do believe you get the same coefficient that I get for the inertial field, which is 1/2. And let me show you I just redid all the computer models. And this, I didn't do the computer models. I had the computer models finally plot out the field. So this is the two tandem SOSOPs, where they're both sitting in the same plane. And their directions of spin are the same. And right now the computer is still considering all the orientations of the target just to be thorough, just in case I miss something. But again, it doesn't matter. Okay, and this outer ring here is your reference. This is what Coulomb's model would give you. That's the normalized value of 1. So this normalized value you see down here, let me show you the full plot of all this information here. Oh, not that one, this one. No. Where did it go? It is inertial full sweep. Okay, so this is the text printout of all the crap down here. Okay, and so what you have here, this is the theta, the angle at which the item is being computed. This is the resultant force vector, and the distance is 1,000 radii is the distance. Okay, so we normalize everything to the radii, and this here, this normal, this would be the effect you would see from Coulomb's model, and therefore the normalized value here, this is just the normalization of the x component only. So if you take the result and divide it by the normalized value, you get what our signature is relative to Coulomb, and if it comes up 1, it'll plot right up against the blue. This gray line here represents 3/4 of the Coulomb amplitude, and this one represents 1/2 the Coulomb amplitude. Okay, and we also have plotted the data for the full effects. This is inertia plus magnetic. Okay, and you can see the blue circle got smaller because there's a lot more energy here. And of course we have data for this as well, tandem full sweep. And I'll publish it. This has got one for every 360 degrees, 0 to 359. So an interesting thing, if we go to the tandem inertial only, and we go to 45 degrees, okay, this gives away the secret here, 45 degrees. Okay, so 45 degrees, our amplitude is exactly half. Our Coulomb component is half, but if you notice, the actual vector is a vector at 1/2 the Coulomb amplitude that goes out at 45 degrees. So in other words, we have a y or a z component of this force. Okay, in the z component at 45 degrees, this z component will be canceled with the corresponding component when we go to 270. So if you integrate this over a full 360 and keep it in vector components, you'll end up getting the right answer with this. So if you just want to consider the stuff in the x direction, this would be the cosine squared of 45 degrees, and that is the answer you should get because that is the component of the force in the direction of the target. Okay, what you're seeing at 45 degrees with your calculation is the full amplitude of the vector that's available at the target. But again, if you keep track of all of the vector components, this component is going to cancel when you get to, I believe it's, 135, that's going to be minus a half, 135. And there's your minus a half at 135. Okay, so you can see there that those components will cancel out. But this is interesting. This means that a target electron is going to induce a wobble in a target electron that averages out over the full rotation. This is interesting stuff. Again, this is one of those things that are thousands of little things all embedded in here that are very interesting that I have not had time to go ferret out. Okay, so there is my answer. I'm grateful for Andreas to do this. I hope I'm pronouncing his name right. I'll post his PDF for the Patreon, and I'll post this this PowerPoint presentation and the full sweep text outputs for you guys to look at. Thank you very much.